Imagine if time isn't what we've always thought it to be. Michio Kaku, a renowned physicist, shook the very foundation of our understanding when he claimed that time does not exist.
Time and space are like a fabric, like rubber, like a trampoline net.
James Webb Telescope proved us wrong. Recent revelations from the James Webb Telescope have added a surprising twist to this discussion.
The whole of the sky was filled with galaxies. This telescope's going to be phenomenal.
This telescope, peering into the depths of the universe, has uncovered something that seems to support Kaku's theory.
The James Webb Telescope has identified 6 galaxies that exist 500 million years.
It's like discovering a whole new layer to the universe we thought we understood. Join us as we delve into Michio Kaku's assertion that the concept of time is non-existent, considering the recent revelations by the James Webb Telescope. JWST's challenge to the Big Bang Theory. The James Webb Space Telescope, launched on Christmas Day 2021, is a larger, more advanced version of the Hubble Space Telescope. Placed in space, it's revealing hidden mysteries from the farthest corners of the universe. Equipped with powerful infrared instruments, it acts like a time machine, letting us peer into the past. Its incredible resolution and sensitivity allow it to spot ancient and faint objects that even Hubble couldn't detect. We're talking about distant galaxies and celestial bodies from the early universe, elusive entities that have been challenging us in a cosmic game of hide and seek. Essentially, James Webb is helping us solve the universe's intricate puzzle, one infrared image at a time. Imagine being in an art gallery admiring stunning pictures taken by the James Webb Space Telescope. You see distant galaxies shimmering across the cosmic canvas. However, among astronomers and cosmologists, there's a mix of shock and disbelief. They're in turmoil, almost as if they're looking at a masterpiece among realistic paintings. Their unease stems from unexpected findings challenging a fundamental theory, the Big Bang hypothesis. This theory suggests the universe began with a massive explosion around 14 billion years ago and has been expanding since. It has long been the bedrock of cosmological understanding, yet the new images from JWST appear to question its accuracy, causing a stir in the scientific community. These captured galaxies aren't aligning with expectations based on the Big Bang hypothesis. They're smaller, smoother, older, and far more abundant than predicted. This discrepancy has researchers like Alison Kirkpatrick, an experienced astronomer, questioning the very essence of their life's work. Surprise and concern among scientists arise from these galaxies' behavior, which challenges the established understanding of the cosmos. Imagine the universe as a giant balloon getting bigger and bigger. According to this idea, far-off galaxies should seem smaller as they move away from us. But here's the twist. After a certain point, they should start looking bigger because their light left them when they were closer. It's a bit odd, but it's an important part of how we think an expanding universe works. Now, the James Webb Space Telescope has thrown a curveball. The images it's capturing show galaxies that are just about the same size as the ones closer to us. It's like expecting faraway friends to look tiny on the horizon, but instead, they're right beside you, as big as life itself. What's even more puzzling is that these galaxies, despite being brighter and having more mass than our own Milky Way, appear 2 to 3 times smaller in these images compared to what the Hubble Space Telescope shows. Adding to the mystery, these galaxies also seem to be moving away faster, indicated by something called redshift. This would make sense in an expanding universe, but these images seem to suggest otherwise. Some scientists noticed this strange thing back in 2014 when they looked at HST images. They found that galaxies with certain redshifts seemed more like they were in a non-expanding kind of space. The JWST is just continuing this odd trend. Even galaxies with really high redshifts, like 12, are showing up looking similar in size. So in simpler terms, the JWST images are making it seem like these faraway galaxies are not affected by the expansion of the universe. This doesn't quite match up with the Big Bang theory, which tells us the universe is expanding. If we stick to the idea of the Big Bang and an expanding universe, it leads to a confusing conclusion. These galaxies would have to be incredibly tiny to make up for the supposed illusion created by the expanding universe. It's a bit like trying to solve a puzzle, where the pieces just don't fit the way we expect them to. JWST's puzzle of unusually compact universes. Consider a galaxy named GHZ2 that the James Webb Space Telescope observed. It's much brighter than our Milky Way, but has been calculated to be only 300 light-years wide. Compare this to the Milky Way, which spans about 50,000 light-years. GHZ2's brightness per unit area would be 600 times greater than the brightest galaxy we see near us. What's even more fascinating is that GHZ2 and other new galaxies are incredibly dense, many thousands of times denser than the galaxies we're familiar with. These galaxies challenge our understanding of the expanding universe and the Big Bang Theory. Astronomers and cosmologists are stirred up by these discoveries because they hint at a different story than what we've thought. Over the years, the Hubble Space Telescope has shown images of many such dense and powerful galaxies, akin to Mighty Mouse from old cartoons. These galaxies pose a perplexing puzzle for scientists, and with the advanced James Webb Space Telescope, the puzzle has only become more complicated. To make sense of these unusually small galaxies, scientists have suggested an idea that's a bit like playing with a magical toy car. This toy car is incredibly small, like a centimeter long, but weighs as much as a real SUV. They propose that these micro-galaxies collide with each other over billions of years, merging to form the larger galaxies we see today. It's as if these toy cars collide and grow into real SUVs over time. However, the James Webb Space Telescope has closely examined these galaxies and found no evidence of such cosmic collisions. If galaxies were crashing into each other, we would expect to see some signs of damage, maybe some disarray or distortion, like a car after a small accident. But that's not what the JWST has observed. Instead, it reveals galaxies that are smooth and neat, resembling the ones nearby. There's a lack of any visible damage or collisions among these galaxies. One study called Panic points out that there are 10 times more of these clean spiral galaxies than theorists had predicted. This discovery is like finding a busy highway with fast-moving cars, but no accidents. It challenges the collision theory. Without signs of galactic mergers, the idea that these small galaxies expanded into larger ones falls apart. If they didn't grow in size, it suggests they weren't small to start with. As a result, the expected optical effects from an expanding universe seem to be missing. Without this expected illusion, the concept of expansion loses support. Hence, there's growing unease among proponents of the Big Bang Theory. The presence of these small, smooth galaxies suggests that the universe might not be expanding, and if it isn't, the Big Bang Theory faces a significant challenge. JWST's clues to a pre-Big Bang universe. Recent discoveries in astronomy have set the stage for a significant reconsideration of our understanding of the universe's origins. The Big Bang Theory has long been the cornerstone of our comprehension of how everything came into existence. It postulates that the universe originated from a colossal explosion. Yet emerging evidence seems to suggest a different narrative, one that could revolutionize our comprehension of cosmic history. Enter the JWST, often likened to a time machine by experts like Michio Kaku. This incredible device possesses the capability to peer billions of years back into the cosmos. Its groundbreaking capacity lies in capturing images far beyond the reach of our naked eye, delving into the infrared spectrum rather than the conventional visual spectrum. What's captivating about these images is their ability to reveal the enigmatic story of distant galaxies. The colors captured by the JWST are not just aesthetically pleasing, they encode crucial information about the ages of stars within these galaxies. For instance, youthful, fiery stars blaze a vivid blue, while their older, cooler counterparts emit hues of yellow and red, akin to our sun. By analyzing these colors, astronomers can estimate the age of star populations within these distant celestial bodies. However, here's where things get intriguingly puzzling. Some of these observed galaxies seem to house stars that predate the supposed age of the universe itself, as per the Big Bang Theory. This discrepancy challenges a fundamental tenet of the theory, as it posits that nothing should exist older than the Big Bang. Moreover, according to the Big Bang theory, as telescopes like the JWST gaze farther into space, effectively peering back in time, there should be a diminishing number of observable galaxies until reaching a point where none exist, a cosmic dark age. However, contrary to this expectation, the JWST's observations suggest a different narrative. Galaxies as massive as our Milky Way were seemingly common just a few 100 million years post the presumed Big Bang event. The implications of these observations are profound. The images obtained by the JWST indicate a startling revelation. There appear to be approximately 100,000 times more galaxies at high redshifts, more than 10 than what was initially predicted. This abundance of large galaxies challenges the established understanding of the universe's formation within the constraints of the Big Bang theory. The emergence of so many colossal galaxies in such a relatively brief time span raises pertinent questions that challenge our existing knowledge. How could these sizable galaxies form and evolve in what was deemed an insufficient time frame according to the conventional model? These groundbreaking discoveries pose a challenge to the foundational principles upon which our comprehension of the universe rests, inviting scientists to re-examine and reconsider our understanding of cosmic origins. Rethinking the Big Bang Theory's 16 contradictions. Recent research has thrown a fascinating curveball into our understanding of cosmic origins, suggesting that the venerable Big Bang Theory might be off the mark on several fronts. It's not just a single or couple of discrepancies. Astonishingly, this theory appears to miss the mark on a whopping 16 predictions, according to recent studies. The only prediction it accurately forecasts is the abundance of deuterium, a type of hydrogen variant. But wait, there's more to this intriguing deviation from predictions. The Big Bang Theory, revered for decades, overestimates the quantities of helium by double and lithium by a staggering 20 times compared to what we observe in the universe. Additionally, this foundational theory stumbles when it comes to explaining the existence of massive structures in the cosmos. According to its principles, these structures should not have had enough time to form since the universe's inception. Adding to the puzzle, the theory struggles with its predictions regarding the density of matter within the universe. And here's an unexpected twist. Remember those supposed asymmetries in the cosmic microwave background that were previously considered non-existent? Well, recent findings indicate that they do exist. It's akin to a cosmic plot twist, shaking the very foundations of our established cosmological understanding. Now, what's the remedy for these cosmic mysteries? Enter the James Webb Space Telescope, a technological marvel that could potentially unlock the answers to these perplexing contradictions. While these discrepancies might seem like small deviations in the vast expanse of cosmic knowledge we've accumulated, they hold immense significance. Each anomaly is akin to a missing piece in our cosmic jigsaw puzzle, obstructing our comprehension of the big picture and leaving us with an incomplete understanding of the universe's nature and origins. These anomalies unearthed by recent discoveries are more than just glitches in our cosmic understanding. They shake the very foundations of what we've long believed about the formation and evolution of the universe. They challenge not just our comprehension of cosmic structures, but also the fundamental fabric of space-time itself. This, in turn, has profound implications for our understanding of universal expansion, gravitational waves, dark matter, and even the ultimate fate of the cosmos. Consider how a seemingly simple discrepancy, like the density of matter, could reshape our entire understanding. If this density differs from our predictions, it could reshape our understanding of how galaxies form and evolve, thereby altering our perspective on the role of dark matter in this process. Similarly, the unexpected asymmetries in the cosmic microwave background could rewrite our understanding of the universe's initial conditions and the speed at which it expanded. But it doesn't stop there. These inconsistencies even ripple into our understanding of time itself. Currently, our perception of time is intricately linked to the evolution of the universe from the Big Bang onward. However, if the Big Bang theory is found lacking, it could prompt us to reevaluate how we perceive time, its flow, and its interconnectedness with space. Challenging the reality of sequential time, The nature of time, a concept deeply ingrained in human understanding, poses a profound question. Does time exist objectively, or is it merely a construct aiding us in distinguishing between moments past and present? Some scientific theories propose a compelling perspective that challenges the conventional understanding of time, an idea suggesting that time might be an illusion fabricated by human memory. This intriguing theory posits that every event, past, present, and future, occurs concurrently. Essentially, everything that has occurred or will occur is happening simultaneously, transcending the linear flow of time as we perceive it. Consider this. While our intuition dictates that time moves exclusively forward, the laws of physics don't inherently dictate such a unidirectional flow. These laws hold whether time progresses forward or backwards. The Big Crunch theory adds a layer to this speculation, suggesting that as the universe ceases its expansion and begins contracting, time might, in turn, reverse. Picture a scenario where the universe shrinks. It grows hotter, akin to a reversed iteration of the Big Bang. The aftermath of the speculated Big Crunch poses an intriguing puzzle. Some hypotheses propose the emergence of a new universe through another significant Big Bang event. Others entertain the notion that our universe might reappear in a different location or form, akin to a cosmic bubble materializing into existence. The implications of these theories hint at a cyclic pattern, a continuum of expansion and contraction, potentially giving rise to an infinite succession of universes. This peculiar possibility challenges the conventional understanding of time, leading some scientists to a bold assertion: time, as commonly perceived, is a human construct. This assertion finds some support in Einstein's theory of relativity, advocating for an interconnectedness between space and time. In this paradigm, the block universe theory, events across all temporal dimensions, past, present, and future, occupy coordinates within a four-dimensional space-time continuum. Essentially, every event retains its reality within this interconnected framework. MIT physicist Max Tegmark beautifully encapsulated this notion, describing our reality as either a three-dimensional arena where events unfold over time, or a four-dimensional framework where everything exists statically, unchanging and immutable. If we subscribe to the latter perspective, time becomes an illusion, with the past, present, and future eternally coexisting. This concept challenges the traditional notion of a linear timeline and invites contemplation on the fundamental nature of existence itself. Barber's spatial theory versus Einstein's space-time. Julian Barber, a British physicist, presents a captivating take on time, envisioning our reality as a series of discrete now moments akin to individual snapshots in a photo album. In Barber's view, each moment stands alone, independent and unique, forming the fabric of our universe. He challenges the conventional perception of the past as a construct derived from our brain's memories. According to Barber, our sense of the past merely arises from our memories, creating an illusion of a linear timeline. In essence, the past might not exist as a concrete entity, but rather as a product of our subjective experiences. Barber elaborates on this intriguing concept through his spatial theory. Within this framework, every now moment occupies a specific place within a vast conceptual landscape he whimsically dubs Plutonia. This landscape, governed by precise mathematical principles, exists outside the constraints of time, transcending temporal boundaries. Here, every point in Plutonia signifies a distinct now, and this landscape embodies a timeless quality, challenging the traditional linear flow of time. This perspective, while revolutionary, draws parallels with the foundational work of Albert Einstein. Einstein's theory of space-time serves as a cornerstone in our contemporary comprehension of the cosmos. His revolutionary insights intertwined space and time, reshaping our understanding of the universe's fundamental fabric. The contemplation of discarding Einstein's concept of space-time might initially appear startling, yet such radical considerations form the essence of scientific progress. Science thrives on revolutions, constantly challenging, refining, and at times entirely replacing existing theories. This perpetual cycle of inquiry and discovery serves as the bedrock of scientific advancement. A glimpse into the annals of scientific history reveals this dynamic evolution. For over a millennium, the geocentric model held sway, positing Earth at the solar system's center. However, Nicholas Copernicus revolutionized this understanding by proposing the heliocentric model, relegating Earth to another celestial body orbiting the Sun. This groundbreaking idea gradually supplanted the long-accepted geocentric model, reshaping our cosmological perception. Following Copernicus, Isaac Newton introduced his seminal work on gravity. Newton's theory elucidated that all massive objects exert gravitational attraction, fundamentally altering our comprehension of celestial motions. This conceptual framework explains Earth's orbit around the Sun and the Moon's orbit around Earth based on mutual gravitational forces. Newton's gravitational theory reigned supreme for approximately 3 centuries, until a watershed moment in 1915. Enter Albert Einstein and his groundbreaking general theory of relativity. Einstein's theory presented a paradigm shift, redefining gravity and space-time. He postulated that massive objects like the Sun warp the fabric of 4-dimensional space-time. According to Einstein, this curvature dictates the paths of celestial bodies, giving rise to what we perceive as gravitational pull. The transition from the geocentric model to the heliocentric perspective, from Newtonian gravity to Einstein's general relativity, epitomizes the continuous evolution of scientific understanding. Einstein's space-time versus quantum's multiverse. Einstein's space-time theory has stood firm for over a century, demonstrating its resilience against numerous challenges. A pivotal moment came in 2015 with the monumental detection of gravitational waves, a triumph that bolstered the credibility of Einstein's general relativity. However, even the most stalwart theories are not impervious to scrutiny. One of the most pressing challenges arises when Einstein's general relativity, built upon the concept of space-time, encounters the realm of quantum physics. These two theories appear to operate under fundamentally different principles, creating a significant quandary within the scientific community. In the quantum domain, the rules seem to diverge from the smooth, continuous fabric of space-time envisioned by Einstein. Quantum mechanics introduces peculiar phenomena. For instance, a single particle can seemingly exist in multiple locations simultaneously. Erwin Schrödinger famously illustrated this with a thought experiment involving a cat, a vial of poison, and a quantum particle tied to a hammer. Until observed or measured, the particle's quantum state implies that the cat is paradoxically both alive and dead at the same time. This intriguing concept clashes with Einstein's vision of a seamlessly interconnected space-time continuum. Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies, highlighted this incongruity. According to Einstein's theory, a gravitational field cannot occupy multiple positions simultaneously. However, quantum physics suggests that matter and energy can exist in multiple states concurrently, leading to a perplexing disparity regarding the nature and localization of gravitational fields. Hossenfelder outlined the challenges of merging general relativity and quantum theory, especially at certain energy levels. Attempts to unify these theories encounter mathematical discrepancies, including probabilities greater than 1, which contradicts fundamental principles in physics where probabilities are bound between 0 and 1. Moreover, at times, these mathematical calculations yield answers of infinity, devoid of tangible physical meaning. This tension between two monumental pillars of physics, general relativity and quantum theory, poses a formidable challenge. The discrepancy between these frameworks at fundamental levels suggests that a seamless unification might necessitate novel insights or potentially a paradigm shift in our understanding of the fabric of the universe at its most fundamental levels. Now it's time for today's subscriber pick. According to renowned physicist Michio Kaku, time does not exist. James Webb Telescope proved us wrong. You see, time's nature has sparked debate about whether it is a real or a human-made concept. Scientific theories propose it as an illusion, with all moments happening simultaneously, defying our linear perception. Physics doesn't insist that time can only move forward. Some theories, like the Big Crunch theory, suggest the universe could contract, reversing time similar to how the Big Bang started. What might happen afterwards varies widely, from new universes forming to our universe starting over. These ideas suggest a repeating cycle, challenging how we see time. Einstein's theory of relativity connects space and time, suggesting they're part of a single four-dimensional framework where past, present, and future all exist together. Physicist Max Tegmark describes reality as this static four-dimensional setup where there's no straight line of time. If this is true, it means time might just be an illusion, changing how we understand our existence. Let us know your take on the contending theories about time. Harmonizing quantum and gravitational realms. In the realm of physics, there's a compelling quest underway, a search for a unified theory that seamlessly merges quantum mechanics and gravity, akin to reconciling two feuding royal families. This pursuit has led theorists into the realm of intriguing and exotic ideas, with string theory emerging as a prominent contender in this domain. String theory, which is one of the most famous theories in this quest, suggests something really interesting. It proposes that the basic building blocks of tiny particles like electrons and quarks are incredibly small, vibrating strings or threads. It's like comparing these strings to the vibrating strings on a musical instrument, where different vibrations or musical notes match up with different particles. What makes string theory enticing is its potential to harmoniously unify general relativity and quantum physics. However, achieving this unity comes with a unique requirement. These strings must resonate across an astonishing 11 dimensions. This encompasses 7 more dimensions beyond the familiar 4 dimensions, 3 of space and 1 of time, delineated by Einstein's theory of relativity. Herein lies the challenge. While string theory holds theoretical promise, there remains a notable lack of concrete experimental evidence substantiating the existence of these additional dimensions. This absence of empirical validation has prompted critical scrutiny and debate within the scientific community regarding the viability and testability of string theory. The unresolved status of string theory, particularly regarding the unobservable extra dimensions it posits, has fueled a wave of skepticism and encouraged physicists to explore alternative avenues in the quest for a unified theory. This underscores the inherent nature of scientific inquiry, a relentless pursuit of theories supported by empirical evidence and experimental validation. Loop quantum gravity is an alternative theory proposed by some physicists that aims to reconcile conflicting aspects of 2 major theories, general relativity and quantum mechanics. Unlike the smooth and continuous fabric of space-time described by general relativity, LQG introduces a fascinating concept suggesting that space-time is not smooth, but is instead made up of tiny interconnected loops. Imagine a piece of cloth. From afar, it appears smooth, but upon closer inspection, you see it's woven from threads. Similarly, LQG proposes that space-time, when examined at the smallest scale, resembles a network of interconnected loops or threads. It's like zooming into a digital photo. What initially appears continuous is composed of individual pixels. However, delving into this minuscule realm poses an immense challenge: the Planck scale. This scale is unbelievably tiny, measuring around a trillionth of a trillionth of a trillionth of a meter. At this scale, the structure of space-time would be so intricate that a cubic centimeter of space could potentially contain more loops than there are cubic centimeters in the entire observable universe. Despite the intriguing implications, proving this concept remains daunting. Current technology falls short in detecting these structural changes at such a minute scale. Physicists assert that testing the Planck scale would demand a particle accelerator 1,000 trillion times more potent than CERN's Large Hadron Collider. To put it in perspective, envision a machine the size of our entire Milky Way galaxy. That's the scale required for probing this unfathomably small dimension. While constructing a particle accelerator the size of our Milky Way may sound like something out of science fiction, a consortium of physicists from the UK, France, and Hong Kong is exploring an innovative avenue to delve into these complex ideas. Their approach involves using an ultra-cold gas composed of billions of cesium atoms, forming what's known as a Bose-Einstein condensate. Their aim? To investigate if gravity might exhibit quantum properties, a radical notion worth exploring. Interestingly, the vast expanse of the universe might provide an alternate method for detecting these tiny space-time structures. Consider the light we observe from the farthest reaches of the cosmos, having traversed billions of light-years of space-time. If there are minuscule imperfections in space-time structure, this light could interact with them. Though each interaction would be subtle, the cumulative effect over immense distances might yield observable consequences. Over the past decade, astronomers have scrutinized light emissions from distant gamma-ray bursts in pursuit of evidence supporting loop quantum gravity. These bursts, stemming from the collapse of massive stars, exhibit intriguing anomalies in their spectral patterns that currently lack explanation. However, whether these distortions arise during the light's journey through space-time or originate from the bursts themselves remains an enduring enigma. Sabine Hossenfelder highlighted this mystery, emphasizing our uncertainty regarding whether these distortions occur en route to Earth or originate from the burst's sources. To unravel this puzzle, transcending Einstein's conceptualization of space-time as a smooth, continuous fabric might be necessary. Einstein envisioned space-time as an unchanging stage, independent of celestial actors like stars and planets. Yet, as we venture into the realm of quantum gravity, a fundamental rethinking of this notion becomes imperative. It's akin to not just altering the script, but reconsidering the very stage upon which cosmic phenomena unfold. Redefining space-time. Laurent Friedel, Robert Lee, and George Hermannik, three forward-thinking physicists, have set the scientific world abuzz with their revolutionary take on space-time. They propose that our conventional understanding of space-time might be limiting, suggesting that it doesn't exist as a standalone entity, but rather emerges from the interactions between objects within it. In simpler terms, imagine space-time not as a separate fabric, but as something that comes into being because of how things interact with each other. This fresh perspective challenges the idea that space-time must be merged with the quantum world. Instead, it asserts that space-time itself arises from the quantum realm. This shift in perspective is precise and groundbreaking, offering a new lens through which we can comprehend the universe. Why is this significant? Well, their theory might hold the key to unraveling a long-standing puzzle in theoretical physics known as entanglement. Entanglement occurs when two particles become intricately connected, so much so that changing one instantaneously influences the other, regardless of the distance separating them. This phenomenon seemingly contradicts Einstein's theory of relativity, hinting at information traveling faster than light, which Einstein famously referred to as spooky action at a distance. However, when viewing space-time through the lens of this emergent theory, things start falling into place. If space-time emerges from the quantum world, then the closeness between particles in a quantum sense becomes more crucial than their physical proximity. It's akin to feeling closer to a loved one far away than to a stranger nearby. In the quantum world, these non-local connections make sense, challenging our traditional notions of spatial distance. Friedel, Lee, and Hermannik have delved into this groundbreaking idea for the past 5 years, cautiously optimistic about their progress. Their approach is appealing as it envisions a quantum world with gravity, a departure from attempts to fit quantum rules into gravity frameworks, as seen in loop quantum gravity. Their next significant step involves incorporating time into their model, a critical aspect in understanding the fundamental fabric of the universe. While this might seem abstract and confined to academic discussions, the implications could profoundly affect our everyday lives. Our comprehension of space-time influences our understanding of both gravity and quantum theory. Consider that our current technological gadgets rely on quantum theory. Therefore, a better grasp of the quantum structure of space-time could pave the way for advanced future technologies, possibly revolutionizing various aspects of our lives. Much like the dethronement of a long-standing monarch, the reigning theory of space-time might soon be challenged. Fresh contenders are emerging in theoretical physics, but it's challenging to predict which theory will ultimately triumph. However, when this scientific revolution does occur, it could herald a new era of discoveries, pushing the boundaries of our understanding of the universe. Thanks for watching, and we'll see you in the next one.